Hello and welcome to part 2 of lesson number 2 in Unit 2, Quadratic Functions, Forms and Transformations, in our grade 11 University College Math class. This is Transformations Part 1, Stretches and Reflections. So the first part of this video we went over exactly how stretches and reflections can be identified in the vertex form of a quadratic, which you see right here. This is vertex form. We're dealing specifically today with the A value. A value is where you find the information about stretches and reflections. We learned that a reflection occurs when the A value is negative. So that's the only thing that the negative tells you. Is there going to be a vertical reflection across the x-axis? And again, we only note this when the vertical reflection is present. If it's absent, i.e. it's opening in the same direction as the parent function, we don't need to mention it at all. Same thing with stretches. If we have an A value that's larger than 1, we would call this a vertical expansion by a factor of A. If it's between 0 and 1, so a proper fraction, we would call that a vertical compression by a factor of A. And if it is 1, we don't even mention it at all, because it's neither an expansion nor a compression. It's in fact the same as the parent function, so we don't need to mention it. So let's work through a couple examples here using our terminology and doing some sketching. So let's look at example A, which is y equals 2x squared. So here we have it. Our parent function, of course, is y equals x squared. So what are the transformations that we see here? Well, we can see that we have a coefficient in front of the squared term. That's our A value. For starters, it's positive. I'd like you to notice that. So this thing is not going to have a vertical reflection. It's going to open up like a cup, same as the parent function. There is, however, an A value that's larger than 1. So we would call that a vertical, actually let's do it in blue, well, we'll do it in green, a vertical expansion. And I want you to get used to using these words because you'll be asked to use them for sure. Vertical expansion by a factor of whatever A is, in this case by a factor of 2. That's the only transformation that's happening. And so now we're going to get down to putting this bad boy on the graph. So parent function, again, just a quick sketch of the parent function would be goes through the origin, out 1 from the vertex, up 1, out 2 from the vertex, up 4, out 3 from the vertex, up 9, etc. So that's the parent function. Again, recall that a vertical expansion means that everything's going to be happening twice as fast. So we're still going to go through the same vertex, but instead of going out 1 and up 1, we're going to be going out 1 and up 1 times 2, which is 2. Now here's a quick little way that we can sort of write this down. I'll just do it up here. Recall that we have 1, 4, and 9, which is when we go out 1 in either direction from the vertex, out 2 in either direction from the vertex, and out 3 in either direction from the vertex. And I want to make a note of that because sometimes people forget this counting that we do, this out 1, this out 2, this out 3, it all happens from the vertex. And this is going to be amplified by our A value. Amplified by A. A happens to be 2 this time. So we're going to have, instead of going out 1 and up 1, we're going to go out 1 and up 2, out 2 and up 8, out 3 and up 18. So let's get that on the graph. Out 1, up 2, we've already got. Out 2, up 4 times 2, which is going to be 8. So let's just move those guys up to 8, 6, 7, 8. And we're not going to have room for the next set. Those will be up at 18. So we're just going to get rid of those. Let's draw the line through, making it curvy at the bottom, curvy up the other side. That's a little pointy, but oh well, we'll be all right. So now that we're doing a little more sketching here, not in the lesson, as part of just an example, let's get some labels on this as well. We always need to be labeling our vertex. That's 0, 0, or any x or y intercepts. In this case, the x and y intercept happen to be the same point. We need to label the function. That's y equals 2x squared. Last but not least, we need to put on our axis of symmetry. This is always a feature. It goes through the vertex. So again, I'm doing this one in orange so you can sort of see it on top of the black. If you can't, if you don't have two different colors, you can kind of just go a little bit beside it just so you can sort of see where it's going. And the axis of symmetry goes all the way top to bottom, and I like it labeled at the bottom, but wherever you have space is fine with me. So there you have a beautiful graph of y equals 2x squared. We've labeled the x and y intercepts, which happen to be the same thing. We labeled the vertex, which happens to be the x and y intercept, and we've got both the function and the axis of symmetry labeled as well. Hopefully that looks okay. Let's give one more example to work through here. So here we have y equals negative 3x squared. So first thing I'd like us to notice is that we have a negative value here out front, and that means that we are going to have a vertical reflection across the x-axis. Reflection across the x-axis. And again, you'll notice that in the last example, we didn't have one, so we didn't mention it. We didn't need to say there's no vertical reflection. We just don't mention it at all. And then if we look at the a value again is larger than 1. Now know what you're thinking here, negative 3 is not larger than 1. The negative's role has already been fulfilled in telling us about the vertical reflection. We're just looking at the number in an absolute sense. So in an absolute sense, 3 is larger than 1, which means that, as with the previous example, this will be a vertical expansion. Expansion by a factor of 3. So again, the negative just tells us about the reflection. The number looked at absolutely tells us that it's a vertical expansion rather than a compression. All right, let's get on the graph here. So maybe before that, we'll just write out here our 1, 4, and 9. Now, I typically write down the 1, 4, and 9. I don't usually write down the plus or minus 1, the plus or minus 2, and the plus or minus 3 that we go out from the vertex. That's sort of something we do every single time. So I don't typically write that down. I'll write it down now since this is kind of the first time we've seen it. And this is going to be amplified by our a value. And again, the a value, yes, it's a negative 3, but the negative insofar as it just tells us there's a reflection. If we're just calculating distance from the x-axis, we can look at that number absolutely. So here we go out 1 and down 3. We go out 2 and down 12. And out 3 and down 27, which is obviously not going to fit on the graph. So let's get to sketching here. The vertex, 0, 0. Out 1 and down 1, 2, 3. Out 2 and down 12. So again, that's a little bit off the graph, no big deal. Kind of measured it out, kind of, sort of, close to where it might be. And now we sketch. So again, we're going to try to make it curvy as we can. Obviously, it looks, as it gets more narrow, it kind of just looks a little bit pointier than maybe you want it to, and that's okay. Let's get the arrows on. Let's get some labels here. So we label our vertex. That's going to be 0, 0. We label our function, y equals negative 3x squared. And we've got our axis of symmetry. Let's get that happening. So that goes through the origin, goes through 0. So again, I'm going to draw it maybe just a little bit beside that x-axis just so people can see it. And then, again, I like it labeled at the bottom, but it doesn't really matter. X equals 0. So there we have our second graph sketched through with the transformations in the right order. Let's do one more example here. So example number 2 is find the stretch factor. So this is if there is an unknown a value, how can we figure out what it is? So we have here the point 312 is on the graph of the function y equals ax squared. Use algebra to find the value of a, the stretch factor. Okay, so a couple of different things that we can do here. If you want to remember that we've been told, and again, this is just kind of a little bit artificial because right now we're just going to be using y equals x squared. We're not actually going to be using this particular function as it is now. It's going to have more stuff in it when we get to day 2 of transformations in the next lesson. But for now, we just have y equals ax squared, and we happen to have an x and y value here. We happen to have a 3 and a 12. So if we substitute that into our equation, so we have y equals ax squared, and we know that y is 12, and we don't know what a is, but we know that this is going to be 3. We can work our way through here and sort of see what we get. So here we have all of our values substituted in. Now let's evaluate and isolate a. So 3 squared is going to give us 9. A, we divide both sides by 9 to isolate a. A then will be equal to 12 over 9, which is 4/3. So therefore, the equation will be so we put back in the y, we put back in the x, but the a we replace with the value we found to be true for a, which is 4/3. So there you go. We've subbed it in and we found the equation. We used algebra to do it. This is how you can find any stretch factor if you know a little bit about the function, either another point, which we don't have in this case, then the vertex, which we do have another point, which is 3 and 12. We substitute it in and isolate the variable we're trying to find. And there you go. That is the end of this lesson. Good luck with the homework. If you have any questions, obviously reach out via email, come to see me in person, our in-room video chat that's open every day. Pop your head in there and I can give you some assistance if you need it. So there's the end of lesson number 2. Good luck with the homework, and we'll see you in lesson number 3 for the rest of the transformations.